All right, so let's take a look at just brief review here of functions and graphs of functions. And the main thing I want to look at is what does it mean to be a function versus a non-function. Okay, so in math we'd say anything that can be described with an equation is a relation. So if I can put in values of x and the equation is going to spit out values of y, that's called a relation. Sometimes it's called a mapping or a pairing. It means input values go in, output values come out. That's what relations and functions do for us. You can almost think of them as machines. You're dumping in the input numbers and they're just spitting out the output numbers. The set of input values, the numbers that we're dumping into the machine, we call the domain. Okay, the domain is the set of inputs, set of x values. Now there's an easy way to remember how those all go together. Well, actually, hang on one second. The set of output values we call the range. Here's how you can remember that they go together. It's all alphabetical. Look, we get input versus output. Domain versus range, and typically the input values are the x values and the output values are the y values. So all three of these go together, input, domain, and x. All three of these go together, output, range, and y. Notice that they're alphabetical. I comes before O, D comes before R, X comes before Y. Okay? So there's an easy way to keep it straight. So a relation becomes a function if we meet one criteria. If for every number that we dump into the relation, it spits out exactly one output value. In other words, for every x value, there is exactly one y value and no more. Okay? If that's true, it's a function. Okay? If that's not true, if I dump in a value of x and it spits out more than one value of y, then it is not a function. Okay, let's look at a couple examples. Here's a relation. Now, first of all, what's the domain in this case? What's the set of values that we're going to dump into the relation? Yeah, -3, 1, and 4, right? And then the range? 3, -2, 1, and 4. Good. So those four numbers represent the range. These three numbers represent the domain. All right, now let's say that here's the mapping. Here's how they go together. When I input the number -3, I get the output value of +3. When I input the value x value 1, I get output y values of -2 and +1. And when I input the x value 4, I get an output value of +4. Okay? Okay, so now I want you to tell me, is this relation a function?
No.
No, it is not. You're right. It's not because of this guy right here, right? The input value of 1 gave me more than one output values, and therefore it is not a function. Okay? So there's the domain. Oh, by the way, we call this set notation. When you get these squiggly brackets around the numbers that are separated by commas, that's a set notation. So that's saying it's a set of values, and those are the three numbers in the set. Okay? There's our range. Function, no way. One is mapped onto two outputs. Doesn't work. How about this guy? So what's the domain?
-3, 1.
Okay. So there's our domain. Okay, range?
3, 1.
3, 1, -2. Okay, now what about this one? Stare at this a second. I want you to tell me here. Is this one a function?
No.
Okay, I'm hearing some yeses and nos. And I can understand why. Maybe both of those answers would come out here. Those who said no, what's the part that looks funny to you? Ah, the 1 and the 3. Yeah, the fact that the 1 and the 3 are both mapped to the same output value. Now let's talk through this, and I'm going to see if you want to change anybody wants to change their mind on this decision. If I input the value x value -3, the relation outputs the single value positive 3. If I input the x value 1, the relation spits out the single value y equals 1. If I input the x value positive 3, the relation spits out the single y value positive 1. And if I input the x value 4, the relation spits out the single y value negative 2. So anybody want to change their minds? What do you think now? Function or not? It is, isn't it? Now the fact that I got these two arrows pointing at a single y value is okay. That's not a problem, because it still passes the test. I still only get one y value for each x value, right? The fact that I happen to get the same y value for two different x values really doesn't matter. Okay. Does that make sense? Yes, sir.
What was your definition of a function?
The function is, a relation is a function if for every input value, aka every x value, it only spits out one output value, so one y value. It's okay if different x values just happen to spit out the same y value. What's not okay is if a single x value spits out more than one y value. Okay? Function. So yeah, it actually works. Each input is mapped onto exactly one output, so we're fine. Now there's a visual test we can do. If we have a graph of a function or a relation, there's a visual test we can do to see if it is or is not a function. Now let's graph these ordered pairs. Oh, by the way, let's just a quick review while we're on the topic here. If we're looking at the xy plane, of course we say that the origin is the point where the axes cross, coordinates 0, 0. And then remember the quadrants go counterclockwise starting in the upper right. So there's quadrant 1, there's quadrant 2 where x is negative and y is positive, quadrant 3 where the x and y values are both negative, and quadrant 4 where x is positive but y is negative. Right? Quadrant 1, everything's positive. Okay. So let's graph these things. If we let's take the first relation that we had, right? We had these four ordered pairs. Remember, we had the domain negative 3, 1, 4, and the range 3, negative 2, 1, and 4. And if we graph these guys, look what we get. Now remember, we said that this one was not a function because we got multiple y values for a single x value. Now how does that show up on the graph? Yeah, okay, so now notice this, where x equals 1, I get two different y values. That corresponds to points that line up vertically, right? And so this is, you might remember talking about the vertical line test. So if you drag a ruler across the graph, if there's any place where the relation lines up vertically, then it's not a function. It fails the vertical line test. Now what about these guys? The second example, look, those are okay. Those are okay. None of those line up vertically. You get different y values for each x value. Now, what about the little issue we had with the same y value being the output of two different x values? When x was 1, y was 1. And when x was 3, when x was 3, y was 1, right? That was okay. All it did was it lined up the points horizontally, but that's okay. They can line up horizontally, they just can't line up vertically. So here's our vertical line test then. If we drag this vertical line across the screen, in that first case, problem's right there. It fails. Okay? So it's not a function. 2 points line up vertically, so it failed. Now this guy's fine. The second one's okay. We can drag it all the way across and points never line up vertically. Okay, so that one is a function. Okay, graphing and evaluating functions. Now, here the graphing part, this is where we're going to start to, the way we approach math is a lot different than it used to be. If you went back 10 or 15 years ago, we would have spent a lot of time graphing functions, making like t-tables. You might remember this, maybe even back in the day, probably back even in grade school when you first got introduced to graphing, you might have done some of this. Remember that remember this stuff, you make an x and a y, and then you plug in values of x and find the values of y. Let's just say hypothetically that here's a function right here. If I plug in x equals 0, what do I get for y? 2 times 0 is 0, minus 7 is negative 7. And so there's a point, right? There's a point with coordinates 0, negative 7 that I could plot on the xy plane. If I plugged in x equals 1, I'd get what? Negative 5. And there's another point that I could plot. You might remember doing this. If I get enough points on there, I can get an idea what the shape of the graph is, and I can kind of just loosely, connect them, right? Not with straight lines, but with a nice smooth curve, unless it is a line like this. Now that works. I mean, and that's something you could always do if you needed to. But now that we live in the age of graphing technology, what do we probably want to do instead? Yeah. Graph it on a graphing calculator, absolutely, because then it's exactly right, and not only do we have an accurate graph, we have an accurate graph that we're going to be able to use on our calculator to do lots of fancy stuff that we'll do throughout the year. I'll show you how to use that technology to answer all kinds of questions just based on the graph that the calculator produces. So we've moved on, and we're not going to spend a lot of time doing this stuff anymore. Instead, what we'd rather do is spend that time learning how can we manipulate that graphing calculator to do a lot of good stuff with the graph. And so the graphing part becomes more automated. Now, we do always know, though, something we want to keep in mind is that an ordered pair is going to be a solution. The x and y values are a solution, of course, if they make that equation true, right? And that's always going to be the case, whether we graph with a calculator or otherwise. So, for example, 2, negative 3 is a solution because it works. If I plug in 2 for x and negative 3 for y, it's true, right? It makes the equation true. Okay. But I could pick another point randomly that didn't work, maybe, and was not a solution because it wouldn't make the equation true. Okay, so in an equation, the input variable is called the independent variable a lot of times. And we'll get into this more as we do maybe like word problems. And the output variable we call the dependent variable. Now this one kind of bucks the system and it's not alphabetical anymore, but you do know at least in this case that I goes with I. Input independent. Okay? Output is dependent. So in this case right here, if we have y equals 2x minus 7, we'd say that x is the input value, so it's the independent variable. Y is the output variable, so output value, so it's the dependent variable. Now this is going to come into play more in situations where we're dealing with like word problems in real world functions. Like say we want to know what's the, we're going to track the growth of a tree as a function of time. So we're going to measure the height, week after week. What are the two quantities I'm looking at there then that I'm keeping track of maybe in my graph? Time and height, yeah. So I want the time maybe in weeks or months or years, I don't know. And then the height measured in whatever units we choose. So of those two units, which one probably is going to be the independent variable and which one is the dependent variable? Now the words are important here. Think what it means to be dependent versus independent. What does it mean? What does it mean to be dependent versus independent? Yeah, so depending on something means that if you depend on somebody else, then what they do impacts you, right? Yeah. If you're independent, though, you're kind of a lone wolf. I mean, you're, right, what other people do is not having an impact on you. So the variable that is being impacted by the other one is the dependent variable. The one that is just going to kind of do its thing regardless is the independent variable. So in that case of measuring the height of a tree, month by month, which of those two variables, height or time, do you suppose, is going to be the independent variable? Time. Yeah, the time's going to pass no matter what. But as time passes, the height of the tree is going to change in a sort of predictable way, isn't it? Right? So height is going to be dependent. Time is going to be independent. And we'll get more exposure to that later. So if we graph an equation in two variables, this is the part that I'm going to kind of skip through because this is what we now do in our graphing calculators. I'll put this PowerPoint up though, as I always do, and it'll be there if you ever want want to look at it. Okay, last thing I want to really get to on this stuff is this function notation. Okay, here's how you read this. People get confused by this, but don't. It's very simple. By naming a function f or g or h or something, we're using just a different way of writing it. Instead of the y, we're going to use this function notation. It's just a fancy way of saying y. So I could replace this whole thing with the equation y equals mx plus b, and it means the very same thing. These are just different ways of saying y. And you might ask, well, why? Just make it complicated for no reason. You know, it's no pun intended there. There is a reason for this. Later on, it makes more sense for us to use function notation because it reminds us what the independent variable is. Okay, the independent variable is always the one that goes inside the function. So in this case, we know that x is the independent variable, and whatever f of x represents is the output variable. And so particularly in cases where we're doing like real world stuff, function notation is a much better way to write it. But that's all it is. Don't make it more complicated than it is. It's just a different way of writing y. Okay, and the way we say it is f of x typically, or we could say the value of f at x, but normally we just say f of x equals mx plus b. All right. Okay, so what about one like this? Decide if the function is linear, then evaluate for x equals -2. This is kind of an awkward question for us right now. As we go further in Algebra 2, it's going to be much, much more obvious to us what linear really means. Obviously, it means that the graph is aligned, but what does it mean in terms of what the equation looks like? Right now, you know, as we're just jumping into a review of linear stuff, and before we've talked about other kinds of functions, you know, we're not really well positioned to make a real formal definition, but there's something we can do that's pretty easy. If it looks weird, it's not linear. If it looks different than y equals mx plus b, then it's not linear. And that's not to say that linear equations can't be written in a slightly different form, but here are the key components of this. If I couldn't take an equation and algebraically make it look like this, then it's not linear. Notice that the only two variables that appear are x and y. Now that could be other variables, but the key things are, what are the powers of x and y here? 1, yeah. There's no square roots, nothing weird like that. There are no exponents, right? No powers of x or y other than 1. Then the only other ingredient is, I've got this number that I can add in there also. Now that could be 0. Maybe it won't even show up. Maybe it's 0. Okay? So those are the characteristics. Are the x's and y's on the bottom? No, they're just normal. They're just on the top to the first power. So is this linear? No. How come? Yeah, right there. There's our red flag. We got that power of 2. So it's definitely not linear. Okay? But we still could evaluate it. If I want to evaluate this thing at x equals -2, what does that mean? You're always asked questions like this on tests and in books, and sometimes we don't ever really take the time to identify or define what that means. What does it mean to evaluate something? What do you think, Katie?
Solve.
Kind of. It's a little different than solve. I think I know what you're getting at, but I don't want to mix those words up, because when we're asked to solve, that means we're isolating a variable, right? When we're evaluating, we're doing something different. What does the word value really mean in math, you suppose? If I want to know the value of a function, or if I want to know the value of a number, or an absolute value, what are we getting at?
Well, evaluate means to give value to.
Okay, to give value to, and for us in math, value means number. We want to know what the number equivalent is, right? So value is number, so to evaluate means we're going to get a number back. We're going to plug in the values of x in this case, plug in -2, the number -2. Every place we have an x, we're going to substitute that -2, and then we're just going to turn this into, simplify it into one big number. Luke, question?
So, would the first one be +2 squared?
No, let's take a look at what this looks like. You gotta be real careful with this. We have to follow order of operations. This ends up being just an order of operations problem, in fact. It's not linear. If we plug this stuff in, f of -2, notice that the -2 is being squared, but not the negative. Because if we follow order of operations, oops, if we follow order of operations, let me go back, I want to do that. If I follow order of operations here, and I'm not isolating, right? I'm simplifying, so I'm going to go top down. First thing I've got to do is everything in parentheses. Well, inside the parentheses, there's nothing for me to do. I've already got just numbers there, right? So I can check that one off. But the very next thing is exponents, okay? So I've got to take the -2 squared before I distribute the negative sign to the answer. So this one's going to look like negative, what is -2 squared? 4. Okay, -2 times -2 is positive 4. Minus 3 times -2 plus 5. So now we did the exponent part and got a 4. Now we can do the multiplication and division. And that's where the negative, I distribute the negative part in.
Okay.
Okay, so now we end up with a -4. What's -3 times -2?
6. 7.
Plus 6. Plus 5. And now we can finally get down to addition and subtraction from left to right. What's -4 plus 6? 2 plus 5 equals 7. So 7's our output, right? Okay? Okay, there's our answer. Okay? Is this guy linear? Is g of x linear?
Yes.
Yeah, there's no red flags there, right? X is to the first power. This is just a fancy name for y, right? G of x is to the first power. So we're fine. It is linear. And if I evaluate it at -2, I'm just plugging -2 in for x, and that's a pretty easy one. -2 times -2 is -4, plus 6 is 2. Good.
Yes.
Okay, good. All right, so. Okay, one quick question for you. Quick question, then we'll be done. Okay, I want to get you thinking just a little bit about lines. And you've done a ton of stuff with lines, it's not going to be new stuff. If I have two lines that are parallel, what can you tell me about the slopes of those two lines? Same slopes. And of course, slope is defined as rise over run. Okay. Now, what if I have, this is the part that people typically have trouble with, so I want to just plug this in today and we'll go back to it. But what if I have two lines that are perpendicular? What then? What's true of their slopes?
Opposite.
The slope is
So let's say we've got line 1. How about y equals m1x plus b1 is perpendicular to y equals m2x plus b2. Right? So what's true of m1 and m2? I think I heard it. Say it again. Opposite reciprocals. Exactly. So we know then that m1 equals -1 over m2, right?
Yeah.
Okay. So for example, what if m1 is -3? What's m2?
3.
No.
No.
1/3.
1/3. There we go.
Good.
I'm never listening to you.
Why would you listen to me?
What if m1 is positive 2/5?
-5.
Oh, bingo.
Bam.
How about this? Okay.
You sure?
All right. That's probably good for one day.
Yeah.